Well, thank you for the warm welcome. And it is warm, isn't it? Reminds me of back home in Louisiana almost, except the humidity doesn't equal the temperature, so we're still ahead of that game. By the way, the speaker who was here last month was Dr. Patton, Don Patton. He just came back from an Israel trip about 2 weeks ago and found out he had a little heart problem, had some stents put in. So we keep him in prayer. I think he's doing well. I didn't have a chance to speak with him. But the other speaker, Dave Prentice, told me about it yesterday in a phone conversation because Dave went on a trip with him. So I think Don's doing well, but, keep him in prayer so that the evil one doesn't take him out of the game. That's the important thing. So what we're going to do this evening, hopefully, is give you some information as best I can present it in a understandable way, because a lot of aspects of this problem get into the technical domain of treating with the physics and so on. And I'm going to try to gloss over that as much as possible. So I hope I'm successful in doing that for you. And if you find that I'm losing you, please let me know. I'd rather know that you're getting lost than to let you stay lost. You know what I mean? So let's move on ahead with this. What accelerated decay rates is the issue that we want to deal with. Can decay rates change? And that's the question. When we speak of accelerated decay rates, we're speaking of a time frame. In fact, decay rates depend upon measuring by some technique a radioactive decay mechanism. That's the kind of decay we're talking about. So it's a time frame, and we're using the amount of radioactive decay that is changed, say, over a given function of time, which is called the rate. Any change with time is called the rate. And so we call that the interval over which the time has spanned for that amount of radioactive decay to be measured. It's kind of like this hourglass that you see up here on the screen, which if you see this little hourglass up here, and right there, it's barely on the screen, but it's there. And an hourglass just has what, sand or whatever. So you want to measure an hour? Well, you watch the sand fall through that top component all the way down to the bottom, and 1 hour has passed, right? If half of it has been moved, half an hour has passed. If a fourth of it has been moved, a quarter of an hour has passed, etc. So this is kind of the thing we're dealing with when we talk about decay rates. So I kind of explained to you what radioactive decay was already, but where does it come from? It comes from the nature of the elements, the chemical elements, the atomic structure of those elements. This is a little bit too far over, but I don't know if we can straighten that out right now. Anyway, every atom has its own unique properties. And those properties determine the kind of atom that it is. And of course, one of the properties that determines an atom is called its atomic number. Another property is its atomic mass. So every atom has a specific atomic number that distinguishes it from another atom. That happens to be the number of protons that are in the nucleus of that atom. That's what that atomic number is. The mass comes from the protons and neutrons that add to the nucleus as well. So the mass can change without the nature or the atomic number changing. And therefore, since the mass can change, we call those different masses isotopes. So the isotopes of any element having a nuclear instability, there are certain rules for instability. That causes that nucleus to be unstable, and it changes. It emanates some energy and maybe releases some particles in the process as a rule, and that's called the decay process. So it changes into some other isotope. What kind of other isotope? Well, it depends upon the nature of the change. But ultimately, it's going to end up with an isotope that doesn't change anymore, which we say is stable. It's ultimately attained. Now, the time for that process, of course, is measured in terms of what we call the decay half-life. And it's important that we at least understand why we use half-life, because we can't ever measure the exact amount of original radioactivity in any substance unless we did it in the laboratory and were able to follow it through on a time clock step for step. But the ages over which they're talking about in the geological sense are supposedly very long ages. You know, some of these half-lives have billions of years in time. So you measure the amount it takes for half an amount of that material to change or to decay, and that's called its half-life. And then another half, that's another half-life, and another half, another half-life, and so it goes. So each interval of change is measured as a half-life from one to the other. And hopefully we'll say this. If you look at it this way, we look at what we call the parent atoms, which are the original ones that are decaying. That's on the blue curve here. And the daughter atoms, or the daughter nuclei, those are the ones that are being changed, or the products of the decay. And that's that red line here. Well, you see in time, but depending on the number of half-lives, the blue, which is the parent atoms, they're losing, of course, going down, 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 because they're being depleted naturally.